Hello, I'm an old guy and I do maths, and today we're going to have a look at the gradient function. And those of you who are edging into calculus will recognize this. Um, you may well be confused by it. The purpose of this video is to explain its origin and how it works, and there'll be a video accompanying this, showing how to use this to differentiate a function. And that's usually called differentiation by first principles. And it is the bane of high school students getting their first taste of calculus. Anyway, this is an extremely clever piece of work. I could never get over just how clever this all is. Okay, so this is the gradient function. Put some brackets in there so that it looks a little bit more like what you're used to. And it says that the differential of x is equal to the function of x plus h minus the function of x over h as h tends to 0. Well, that's going to take a tiny bit of explaining. So let's get to a diagram. Now, let's just imagine that you have a curve on a Cartesian plane, and you're interested in the gradient of this curve at this point. So the gradient would be the slope of a tangent just touching the curve at this point. And one of the ways in which you could figure this out is by taking two other points on this curve and finding the gradient of the line between them. So you could find the gradient of this line, and hopefully you've approximated things sufficiently that it's a pretty fair indication of what this gradient might be. Now, the point of the gradient function is that it says pretty much that if you get these points converging on this point, so say this point is down here somewhere, and this point is up here somewhere, it's much, much more likely that you'll get an accurate read on what the gradient of this point is. It won't necessarily be exact, but as these points come in and the distance between them converges on 0, you will get a more and more accurate reading of the gradient of this curve at this point. Okay, so we could talk just about gradients, and how you find the gradient of a line is this old gem, y2 minus y1 over x2 minus x1. And what you're going to see is that the gradient function is a very clever reworking of this. So let's get back to the starting page and look at the bit that you didn't see. So here's the gradient function, and here's a little illustration of it in action and what things mean. So let's start with the x-axis first. We have this curve, and the points that we're interested in are the points generated by a value of x, which we would refer to as the function of x. So this could be x, this is the y-axis, and we would get a coordinate x, y. If we put x into the function of x, we'd get this coordinate x, y. which we can also write as x function of x. Okay, and if we moved along here a distance of h, I don't know why it's called h, but we'll move from here to here and we'll call the distance h. This point here is x plus h, and therefore the y value up here is going to be the function of x plus h, just as this was the function of x. Okay, so we could write this as x and y again, and because we've got two of them, we might write x2 and y2, and we might call this x1 and y1. But we could also write this as x plus h, which is the distance from that we've added to get to here, function of x plus h. Okay, now think back to this. For y2, we could put function of x plus h. For y1, we could put function of x. So very, very roughly, function of x plus h, that could be y2. Function of x could be y1. And x2 would be x1 would be x plus h, so that's x1. X2. Say that again. x2 could be x plus h, and x1 could be x. So that's x1. So basically what has happened is we've just substituted a notation in a standard gradient formula for the y values and the x values. Okay, so far we've got this, which I have written out more neatly here. y2 minus y1 over x2 minus x1. And this is our gradient function with a tiny bit of work. This and this we can cancel out, and this is what you recognize as the components of the gradient function. Now, there's one other thing to take into account. H tends to 0. What does that mean? Well, let's go back to this illustration, and I'm sorry it's getting a little bit busy, but let's say that our point of interest is there. We're actually looking for the gradient of that. And what this function says is that as these 2 points close in on this point, we get an incredibly accurate reading of what the gradient of this line, this curved line, is at this point. And gradients, as you know, are calibrated in rise over run. And so we have one problem to overcome, which you will see when we do this using a function. We don't want this denominator to be 0 ever. So one of the things that we have to do when we use a practical example of this is that we have to get rid of this, and there's a way of doing that. So just don't get too concerned about that. We're not going to have a denominator of 0. But all I really want to get across in this video is that this is a rewrite of an ordinary gradient equation where the distance between the 2 points that you're using to find the gradient of a line connecting two other points. So the gradient of the line connecting these 2 points converges on the point of interest, and at a critical moment becomes 0, and we get the gradient of this point. It's easier to understand when you see it in action, and so at the same time as I do this video, I've made a video on differentiation by first principles using this. I hope this unconfused you a little bit. I do hope it didn't confuse you more. Thanks for watching. See you next time. Bye.